Okay, and we're back. The last couple of videos we talked about work and what work means. In the context of physics and energy, work is simply the transfer in energy from one object or system to the next, or between two different types of energy. And we haven't really talked about what types of energy we're talking about, and that's what we're going to do today. So as a review, work is energy transfer between objects or systems or types of energy. If you're confused about the types of energy thing, because we've been talking about this for a few videos, imagine like you open a bank account or you have a couple of bank accounts open and you can transfer money between the two bank accounts, like a checkings or a savings account. Okay, it's kind of like that. You still have that energy, it's just changing where it's stored. Now, let's be more specific. What are these types of energy that we're going to talk about? We're going to study four. The first one is kinetic energy, as you can see from the title right below this. If you look on the rest of the reference tables, you'll see some other types. You'll see gravitational potential energy. You'll see a third type called either spring potential energy or elastic potential energy. You'll hear me refer to it as both. So there's two different types of potential energy, so notice that we have to be clear about which type we're talking about. And the fourth is called internal or thermal energy. Now, these first three, kinetic energy, gravitational potential energy, and spring or elastic potential energy, those are the types we're going to be talking about in this and the next video because those types are more related. They're more closely related than they are to internal thermal energy. And that's because they're all different types of what we call mechanical energy. The thing with mechanical energy is you can very easily transfer mechanical energy back and forth between the different types. You can very easily transfer kinetic energy into gravitational potential energy, into elastic potential energy, and then back to any of those types. However, you cannot as easily transfer any of these types of energy to internal or thermal energy, and once it becomes internal thermal energy, you can't put it back into these other types. And we'll talk about why that is later on. Anyways, those are the four main types that we're going to study. Okay? The first type, kinetic energy, the definition of it is energy associated with, if you can probably guess this, motion. Energy associated with motion. In other words, moving objects. Moving objects have kinetic energy. Non-moving objects don't have kinetic energy. How does an object's kinetic energy change? Well, it changes because work is done on the object. Okay? Some work is done by a force, and it changes the kinetic energy of the object. I'm not just going to tell you the equation for kinetic energy, even though we can look it up on the reference tables. Instead, I'm going to derive it for you. I'm going to show you where it comes from. It's kind of a weird derivation, okay? And you're not expected to know this, but I do like to show it just in case you're interested. Let's start with this. If we're looking for the net work done on an object, then that would be equal to the net force on an object multiplied by the displacement, multiplied by the cosine of theta, but that's just going to end up being 1. Okay, so the net work equals the net force multiplied by the displacement. Okay, the total amount of work, transfer of energy that's going on with an object or system is equal to the net force on that object or system multiplied by the displacement, how far that object or system moves from its starting point. Now we know that the net force is equal to m times a. So I'm going to write that in. I'm going to change that equation. So now I have m times a times d. In other words, we could say that the net work done on a system is equal to the mass of the system times the acceleration of the system times how far the system moves. Now I'm going to go to something completely different for a second, so stay with me. One of the kinematics equations looks like this. Vf squared equals Vi squared plus 2AD. I want to solve this equation for A times D. In other words, I want to get A times D alone by itself. In order to do that, I'm going to subtract VI squared to the other side, and I'm going to divide by 2. So subtract VI squared. I end up with VF squared minus VI squared equals 2AD. Divide both sides by 2. And that's what I end up with. VF squared minus VI squared over 2 equals AD. Now, the reason I did that is so I can plug this in here. And again, I'm not expecting you to understand why I'm doing this right now, but to follow along the algebra. M times VF squared minus VI squared over 2. Now, I want to distribute that M to both of these terms. So I could say that the net work equals MVF squared minus MVI squared over 2. Or here's what I'm really going to do. I'm going to pull the 2 outside as well. And I'm going to write it in this form. The net work done equals 1/2 times M. And that 1/2, because I can pull the 2 out because that's in both terms, the 1/2 times M is going to be distributed to both VF squared and VI squared. So I have 1/2 M VF squared minus 1/2 M VI squared. Now, what you notice here is we have very similar looking terms here. I have this term that is 1/2 M times a velocity squared. If you look at the reference tables, we haven't looked at this in a little bit, so let's look. Notice that I have work equals FD. Notice, like I said, they don't have cosine theta on there, but you need to put that on there. Equals delta ET, change in energy, transfer of energy. So there's your work equation. And right above it, we have KE equals 1/2 mv squared. KE is kinetic energy, M is mass, V is velocity or speed squared. So this term right here, or both of these terms, I could call this, since this is V final, I could call this the final kinetic energy term. I could call this the initial kinetic energy term. From this, I get that the net amount of work that's done on an object is equal to the change in kinetic energy. The more important part for you guys is that this term, 1/2 mv squared, is equal to the kinetic energy of an object. That's important. That's one of the most easy to remember equations that you're going to see this year. Not because it's necessarily easy, but we're going to use it so many times that you are going to remember that kinetic energy is 1/2 mv squared. I promise. So, we see from this derivation that we have this term called kinetic energy. Objects that are moving have kinetic energy because they have a velocity. And the kinetic energy is equal to 1/2 times m times v squared. The units of energy are the same as the units for work. They are joules. And this is scalar. In other words, energy does not have a direction associated with it. Okay? Now, again, derivation, it's a little complicated, a little all over the place. The key thing is that you know this. The kinetic energy equals of an object equals 1/2 times its mass times its velocity squared, and that the net amount of work done on an object changes the kinetic energy. It's equal to the change in kinetic energy. So for the first example, how much kinetic energy does a rowboat and man with a combined mass of 155 kilograms moving at 5 meters per second have? Well, calculating kinetic energy by itself is very straightforward. Okay? You guys are used to calculating like this by now. The kinetic energy is 1/2 times the mass, 155 kilograms, times the velocity of 5 meters per second squared. Half times 155 times 5 times 5. The kinetic energy of this system, the man and the rowboat combined, is 1,937.5 joules. Very easy to calculate. Let's take this up a step. The rower exerts a force of 40 newtons on the oars over the course of 2.3 meters. So a rowboat, you got to push back on the water to go forward. He's exerting a force of 40 newtons while the boat moves 2.3 meters forward. How much work was done by this motion? Okay, well, him putting a force on the oars, that's an applied force. So the work done by that applied force equals the applied force times the displacement times the cosine of theta. Now, his force is propelling the rowboat forward, the displacement's going forward, so they're in the same direction. Therefore, we have an applied force of 40 newtons multiplied by the displacement of 2.3 meters times the cosine of 0 degrees, since they're in the same direction, which means 1. The work done by the applied force is 92 joules. In other words, 92 joules of energy were transferred into the system. Where were they before? They were stored as energy in the man's muscles. Okay? That's a different type of energy we're not going to talk about. It's chemical energy, but it's stored in the man's muscles. He uses that energy and gives it to the rowboat and him. Now, what form is it in once he gives it? Okay? Once those 92 joules of energy are transferred to the man in the rowboat. Well, think about it. If you pull on the oars, you're going to go forward. So, since the work done is equal to the change in kinetic energy, that's the type of energy that's changing in this case, we can say that this is equal to the final kinetic energy minus the initial kinetic energy. The work done was 92 joules. The final kinetic energy is what we're looking for. And the initial kinetic energy we just solved for was 1,937.5 joules. We solve for the final kinetic energy by adding this term over to the other side. And we get that the final kinetic energy is 2,029.5 joules. That's the final kinetic energy. From that kinetic energy, we can find the final speed of the man and rowboat. Remember, the mass was 155 kilograms. Now the kinetic energy increased, so what can we expect to have happened to the final velocity? Should it be bigger or smaller than the initial? I would guess, since the kinetic energy increased, that it should be bigger. And it would turn out to be exactly right. Divide by half, divide by 155, take the square root. It did increase just a little bit. 5.12 meters per second is the final velocity. Now, just a couple of good concepts and facts to know about kinetic energy. Can it ever be negative? Let's explain. Well, think about the equation. Ke equals 1/2. And notice, Ke are not two variables. It's one variable. It's called Ke. 1/2 mv squared. We've never had a negative mass. That would be really weird. And velocity, even though velocity is a vector and it could be negative, what happens when you square a negative, when you do a negative times a negative? If I have -7 times -7, I get positive 49. So even if I have a negative velocity, the square makes it positive. 1/2 is positive, m is always positive, v squared is always going to turn out to be positive. Can kinetic energy ever be negative? No, because m is always positive and v is squared. Kinetic energy will always be positive. To the right, sketch a general graph of Ke versus v. How does the kinetic energy change as the velocity increases? Well, you might be tempted to guess one way or another, but why don't we prove this? Instead of having to guess it? We can use this equation, Ke equals 1/2 mv squared, in order to calculate a whole bunch of different kinetic energies if we assume a certain mass. I'm going to do a little trick here. Let's assume the mass of 2 kilograms. Let's say we have a 2 kilogram mass. Let's make a little chart, little data chart. So I have V and Ke. I'm going to have a whole bunch of different values for V, and we're going to calculate what the kinetic energy is for each. Okay? Now, The nice thing about assuming a mass of 2 kilograms is 1/2 times 2 kilograms is just going to be 1. So in this case, once we square v, we're going to have what kinetic energy is because we're setting our mass to be something convenient for us. It's not always going to work out like that. It's only if you have a mass of 2. So v squared would be 0. 0 times 1 is 0. No velocity, no kinetic energy. If you're not moving, you don't have kinetic energy. Okay? That's the definition. Don't think kinetic energy is anything else. It just shows you if an object is moving or not. If the velocity is 1, 1 squared times 1, well, that's just simply 1. Seems kind of linear so far. 2 squared times 1 is 4. Now that doesn't seem linear anymore. Okay? Jump of 1 joule between 0 and 1, and then 3 joules here. What about 3? If the velocity is 3, we do 3 squared, which is 9, times 1 times 2 is, or 1/2 times 2 is 1. So 9 times 1 is 9. Yeah, that's definitely not linear. 4 squared is 16. 5 squared times 1 is 25. Look at this pattern. The velocity goes up by the same amount each time, but the kinetic energy is going up different amounts each time. Matter of fact, the amount it's going up is getting bigger and bigger. What does that graph look like? Looks like this. It's parabolic. Okay? Now, could you have guessed that? Absolutely. Ke versus v, the v has a squared on it. That's your clue right there that this is a parabolic graph. Don't tell me it's exponential, by the way. So it curves because of the v squared. Kinetic energy is very simple. Okay, it's very, very straightforward. Gravitational potential energy is also kind of straightforward, but there's a little bit more we can do with this. Gravitational potential energy is defined as energy associated with height above a massive object, such as Earth. Okay? We calculate in this class the gravitational potential energy because of Earth. In other words, the fact that Earth is massive allows objects to possibly have some energy if they are some height above the Earth. Why is that? Because think about what the Earth does. If there's some height above the Earth and we let go of them, they fall. They weren't moving in the beginning. Then they fall and gain some energy. That energy must have come from somewhere. We call it potential energy because this is energy that objects have due to their position. They have it due to their position above, some height above the Earth. Okay? So, how does an object gain gravitational potential energy? It changes its distance, not by itself, something changes its distance, or in other words, it changes its height from the surface. Okay? Objects gain gravitational potential energy or lose gravitational potential energy when their height above the surface changes. All right, so this is another type of energy that we're talking about. It's a type of energy that has to do with their position above the Earth's surface. Okay, that's another type of energy they can have. Here's the equation or derivation. The theme here is going to be if we're lifting an object. If we're picking something up. If you're lifting an object, then the forces on that object while you're lifting it might look something like this. Here's your object. Here's your axis. You're exerting an applied force upwards. There's a force of gravity downwards. You're lifting the object up, so I'm just going to put in the displacement is upward. The net force in the y direction looks like this. F net y equals Fa minus Fg equals MAy. Let's make the assumption, let's make this as simple as possible, that the acceleration is 0. You're picking this up at a constant velocity. Therefore, the applied force is equal to Fg, and I'm going to just change this out. It's equal to mg. Let's say you want to know the work done by your applied force. That would be Wa equals Fa times d times the cosine of theta. Well, the applied force we found was equal to mg. Notice I don't have any numbers here, but that's fine. I'm just looking for an equation. I'm trying to show you what the equation is. That's what a derivation is. We're finding the equation, okay? Equations don't just pop out of nowhere. There are reasons that we have these certain calculations to make. mg times d times the cosine, let's see, d and FA are in the same direction, so it's the cosine of 0 degrees. That's going to be 1, so I have mgd. Now the displacement is where it ends up minus where it started, okay? Remember, it's the straight line length from where the object's final position back to its initial position. Final minus initial. So you could think of this. The displacement here is really the final height, because we're lifting it up, remember, minus the initial height. If we do final height minus initial height, that would show us the displacement. Imagine if I had something at 1 meter off the ground initially, and I picked it up and lifted it to 3 meters off the ground. Well, what would that mean? That would mean that the displacement was 2, but if I do 3 meters minus 1 meter, well, that's a displacement of 2. I'm going to distribute this so that I get mghf minus mghi. Now, notice that again, I have similar terms here, mg times h, mg times h. That is your clue that that is important, okay? As a matter of fact, mg times h is equal to the gravitational potential energy, PEG. And you have to have the g on here because we need to talk about this as gravitational, mgh. And so this would really be the final gravitational potential energy minus the initial gravitational potential energy. So I could say here that the work done by the applied force equals the change in gravitational potential energy. So I could also write this. The gravitational potential energy is mgh. The change in gravitational potential energy is equal to m times g times delta h. Now that is what is in your reference tables. mg delta h equals the change in gravitational potential energy. Why is that? It's a little bit above your level at Regents, but it's the change in gravitational potential energy is actually more important than just gravitational potential energy by itself. And you can see that equation here, delta PE, they really should have a G here, equals mg delta H, right above the kinetic energy equation. Okay? So just a couple notes here. D is, I'll do this, is the displacement from initial height to the final height, which means that D is equal to HF minus HI. Remember, H just stands for height. And lastly, in this case, we see that the work done transfers energy from person into the gravitational potential energy of the object that we're studying, that we picked up. Okay? So in this case, we have a situation where energy is being transferred. If you're lifting up an object, the energy was initially in your muscles, stored as chemical energy. We're not really going to talk about that too much. And it was turned into gravitational potential energy by the applied force. You exerted an applied force, and your energy from your muscles converted into the gravitational potential energy as that object went up, as it changed its position from the ground. Key takeaways: gravitational potential energy is equal to the mass times the gravitation times the acceleration due to gravity times the height of the object above the ground. When we come back, we'll look at some examples with gravitational potential energy because there are a couple of tricky parts, and then we will talk about some other stuff. Okay? Talk to you later.